Okay, so this is Lauren, Physics 350, Homework 7, problem number 1. So we have a long rod of radius A, and then we've got polarization like right here. It's KS in the S hat direction. We're neglecting end effects, saying that the cylinder is long. So our first task is to calculate the bound charges, sigma B and rho B, and then what are the units of K. So from Griffiths 4.11 and 4.12, we have these two equations, and then it's just math. So I just mathed, and then got that. And then for rho, we know that there's no theta or z dependent, so we just have this term, and then I just did math again, and then got that. So I think we're good. And then K has to have the same units as rho, because of this. I just have a -2 and a K, so rho has to be the same units as K, so they have to be coulombs per meter cubed, because those are the units of rho. Okay, so then part B, we have to use those things to find the electric field inside and outside the cylinder. So that's this thing right here. That's Gauss's law, which it tells us to use in the problem. So then outside we have these things here. We have the two bound charges times the area and the volumes, depending on which one I use. And then I substitute the values that I got before. And we know that the area is this, the surface area is this one here, because we don't have the end effects, so we just have the actual like cylinder part, not the end caps. So the areas and the volumes, and then the two values that we found from part A. We know Q enclosed is 0, so that means the electric field has to be 0, and 0 doesn't have a direction, so that's the end of the story there. Then inside, we have this again, and then we integrate an exact differential and get this, and then we know that the electric field has to be this. So then Q enclosed is going to be the rho bound charge times the V, which is this part, and then we just substitute it in and solve for E, and we get that lovely thing right there in the S hat direction. Okay, and then we have part C, which is find the electric displacement field inside and outside the cylinder. So that's this right here when you take inside and outside, which is what those two things are. So outside we just do math and we get that, and then inside we do math and we get that, and that's all.